Hello everyone. This is our first lecture for Chapter 11, Two Samples, Hypothesis Testing. Here are the learning objectives for Chapter 11. This is what we are going to cover, and this is what you will need to know for the next proctored quiz. Think of these learning objectives as your roadmap through the chapter and your study guide for the next quiz. So take a minute, hit the pause button, and read through these. In this lecture video, we will continue to explore inferential statistics. We will focus on two samples hypothesis testing. Specifically, we will discuss independent samples designs and how to conduct an independent samples hypothesis test. Here is an overview of Chapter 11. Up to this point, we have discussed and learned how to determine the relative position and probabilities of individual scores in a distribution with known population means and standard deviations with z-scores. We have learned how to conduct one-sample z-statistic and t-statistic hypothesis tests, z-tests with known population means and standard deviations, and t-tests with hypothesized population means and sample standard deviations as estimates for population standard deviations. Now with Chapter 11, we start looking at inferential statistics that we typically use in research. Most research studies compare two or more sets of data. Data from two completely different independent participant groups are called independent samples, independent measures, or between subjects design. Data from the same or related participant groups are called related samples, paired samples, repeated measures, within subjects, or matched subjects design. The statistical procedures are considerably different for these two designs, independent samples and related samples. Each design has different strengths and weaknesses. So we will begin with independent samples design, and then in the next video we will discuss related samples design. Independent samples designs allow researchers to evaluate the mean difference between two populations using data from two separate samples. The identifying characteristic of the independent samples or between subjects design is the existence of two separate or independent samples. This way, an independent samples design can be used to test for mean differences between two distinct populations, such as men versus women, or between two different treatment conditions, such as drug versus no drug. Samples are independent if participants in each sample are not related in any way. Samples are considered independent with two different designs. As you can see in this first design, samples are randomly selected from two separate populations. We randomly select a sample from population A, and we randomly select a sample from population B. These populations are independent and not related to each other in any way. This type of sampling is commonly used to conduct quasi-experiments for situations where levels of a factor or independent variable are pre-existing. For example, let's say we hypothesize that students who pay for their own college education without financial assistance will study more. We record the time spent studying in a sample of students who, prior to the study, were paying their tuition with or without financial assistance. Population A consists of students who pay for their college education with financial assistance. Population B consists of students who pay for their college education without financial assistance. Each sample is selected from a different population, so each sample constitutes a different group. Here are two more examples. 1. Do males and females significantly differ on their level of math anxiety? The independent variable is gender with two independent groups, males and females. The dependent variable is level of math anxiety. Number 2. Do older people exercise significantly less frequently than younger people? The independent variable is age with two independent groups, older people and younger people. The dependent variable is frequency of getting exercise. In this second design, participants are randomly selected from one population and then randomly assigned to one of two samples, which could be experimental and control groups. Just like in our first design, there is no overlap between the two groups. Participants' scores are independent and are not related to each other in any way. This type of sampling is commonly used in experiments that include randomization, manipulation, and a comparison or control group. The only way to achieve an experiment is to randomly assign participants selected from a single population to different groups. For example, let's say we hypothesize that paying students for earning higher grades will improve their performance on an exam. To test this, we could select a group of students and have them study a word list and test their recall. In one group, participants are paid for better scores, and in a second group, participants are not paid. The population would be college students, where one sample was selected and participants were randomly assigned to be paid, group 1 or the experimental group, or not paid, group 2 or control group, for earning grades. Here are two more examples. 1. Does migraine pain lessen for patients who get drug A compared to patients who get a placebo? The independent variable is amount of drug with two independent groups, the drug and placebo group. The dependent variable is a measure of migraine pain. 2. Is quality of life different for people who meditate compared to people who do not? Independent variable is amount of meditation with two independent groups, meditators and non-meditators. The dependent variable is quality of life measure. As with all hypothesis tests, the general purpose of the independent samples t-test is to determine whether the sample mean difference obtained in a research study indicates a real mean difference between the two populations or treatments, or whether the obtained difference is simply the result of sampling error. Remember, if two samples are taken from the same population and are given the same treatment, there will still be some difference between sample means. This difference is called sampling error. The hypothesis test provides a standardized formal procedure for determining whether the mean difference obtained in a research study is significantly greater than would be expected by sampling error, or if the null is true. To prepare the data for statistical analysis, the first step is to calculate the sample mean M and sum of squares SS, or sample standard deviation S, or sample variance S squared, for each of the two samples. The hypothesis test follows the same four-step procedure we outlined in Chapter 9. Step 1. State the hypotheses. For independent samples t-test, the null states that there is no difference between the two population means. On this slide, I have provided the hypotheses for upper-tailed tests, lower-tailed tests, and two-tailed tests. You will notice that there are two different ways that you could state these hypotheses. For two-tailed test, the null states population mean 1 is equal to population mean 2, or it states population mean 1 minus population mean 2 is equal to 0. Both of these are the same. They are just stated differently. Step 2, set the criteria. Select alpha. Remember, in our class, this will always be given to you. Locate the critical region. The critical values for the t-statistics, or the t-statistic, are obtained using degrees of freedom that are determined by adding together the degrees of freedom for the first sample and the degrees of freedom value for the second sample. As you will see later, this formula is the same as the denominator of the pooled variance. Step 3. Calculate the test statistic. The t-statistic for the independent samples design has the same structure as the one sample t introduced in Chapter 10, where t is equal to sample statistic minus the hypothesized population parameter divided by estimated standard error. However, in the independent samples situation, all components of the t formula are doubled. There are 2 sample means, 2 population means, and 2 sources of error contributing to the standard error in the denominator. In the formula for an independent samples t-test, we subtract the mean difference between the sample means M1 and minus M2 from the mean difference stated in the null, mu1 minus mu2, which is actually always equal to 0. This simplifies our numerator so that we just have to calculate the mean difference between the sample means. We then divide the difference by the combined standard error in both samples, called the estimated standard error of the mean difference. The estimated standard error of the mean difference measures the average distance between sample mean differences M1 minus M2 and the population mean differences mu1 minus mu2. How much difference should we expect between 2 sample means if the null hypothesis is true? The formula on this slide can only be used if sample size n for group 1 is equal to sample size n for group 2. N1 equals N2. In this case, we do not need to weight each sample variance by its respective degrees of freedom. We can go straight to calculating an estimated standard error. We divide each sample variance S squared by its respective sample size n. Add the 2 results together and then take the square root. To find estimated standard error of the mean difference in the denominator of our t-statistic, you need to calculate S squared p, which is pooled sample variance. Remember that S squared is sample variance, and adding a small p in the subscript makes this pooled sample variance. A pooled sample variance is the mean sample variance for 2 samples. When the sample size is unequal, the variance is a weighted mean so that the pooled sample variance is weighted toward the sample mean calculated from the larger sample size. The larger n is, the better the estimate of sample variance will be. The formula for calculating sample variance when the sample size is different in each group is pooled sample variance equals sum of squares from sample 1 plus sum of squares from sample 2 divided by degrees of freedom from sample 1 plus degrees of freedom from sample 2. The second formula is equivalent. pooled variance equals variance times degrees of freedom from sample 1 plus variance times the degrees of freedom from sample 2 divided by degrees of freedom from sample 1 plus degrees of freedom from sample 2. This is not, and I repeat, this is not estimated standard error. We're not done yet for the denominator. Now that we have pooled sample variance, we can finally calculate estimated standard error of the mean difference. We substitute pooled variance and sample size in the formula. So estimated error, we divide pooled variance S squared P by each sample size, add the two results together, and then take the square root. We can now calculate the test statistic for independent samples t-test. We take the sample mean difference and divide by estimated standard error of the difference. This gives us the obtained or calculated t-statistic. Step 4, make the decision. To decide whether to reject or fail to reject the null hypothesis, we compare the obtained or calculated t-statistic to the critical value. If we reject the null, we must provide a measure of effect size. Effect size for independent samples T is measured in the same way that we measured effect size for one sample T in Chapter 10. Specifically, we can calculate an estimate of Cohen's d, or you can calculate R squared to get the percentage of variability explained by the independent variable or by the treatment effect. When estimated Cohen's d is used with independent samples t-tests, we place the difference between the two sample means in the numerator and the pooled sample standard deviation, or square root of the pooled sample variance, in the denominator. Another measure of effect size is the proportion of variance or variability in a dependent variable that is explained by the independent variable or the treatment. Percentage of variability is calculated using the same formula for both one sample and independent samples t-test. Effect size can also be calculated using confidence intervals. Same as we did for one sample t-test in Chapter 10, we find the interval estimate, reported as a confidence interval, and stated within a given level of confidence, which is the likelihood that an interval contains an unknown population mean. Using sample mean difference, we calculate the confidence interval by adding and subtracting a margin of error, which is obtained by multiplying t critical value and estimated standard error. One last slide for independent samples t-tests. The assumptions that must be met in order for us to conduct an independent samples hypothesis test are the same as the assumptions for a one sample hypothesis test plus one. The three same assumptions are random sampling, independence of observations, and normal population distribution. The new assumption is that the two populations must have equal variances. This is called the assumption of homogeneity of variance. In order for us to be confident in our results, the populations we are sampling, or the populations we are sampling from, must have equal variability. This assumption is usually satisfied when the larger sample variance is not greater than 2 times the smaller. So large variance divided by smaller variance has to be less than 2. In the next video, we will discuss related samples design and related samples hypothesis tests.